Thank you all for coming to Journal Club. This is, as I was announced, this is going to be a two-part series on Fourier transforms and quantum computing. And as I advertised this week, we're going to see a live demonstration of Shor's algorithm at the end. But first we have to go through kind of, all this other stuff kind of before we get to the punchline for this week. So this week we're going to be talking mainly about the discrete Fourier transform and how it applies to Shor's algorithm. And then next week we'll be talking about the non-abelian Fourier transform and some kind of modern algorithms for that. Last week, this week is going to be a paper from 10 years ago, over 10 years ago at this point, but it's my favorite paper of all time, so I get to share it in Journal Club. And then next week we'll be seeing a paper that's a little more modern. And so I don't know if this has ever irked you guys about like Fourier analysis as it's taught, but it's really like two different things, right? First we have the Fourier series, where if we're given some kind of periodic function on R, right? Some kind of periodic function, its Fourier series is going to be just a set of, like a discrete set of coefficients, right? And it satisfies this kind of squaring identity with the original function. But if we have a non-periodic function, then its Fourier transform is this other function on R. So we go, like, what's this connection between being periodic and discrete and being non-periodic and being continuous? They seem very similar. They look like they should be somewhat related. My question to you is, how exactly are these related? And so in general, we can treat periodic functions as just functions on a circle, because you just take the period and you just wrap it around, right? And so, of course, corresponding Fourier series is going to be a function on the integers. And so there's this kind of underlying connection I want you to believe between the circle and the integers, and between the real numbers and itself. And so what is this connection that lets us define the Fourier transform in the first place, and how can we use this to possibly extend it to other groups? And so I want you to ponder it a little bit, because it's not obvious at all. But the answer is this thing called Pontryagin duality, where it's a duality between abelian groups, where I'm going to have to explain. An abelian group is just a set with an addition operation that obeys all these things you kind of expect from addition, including this last one. And next week we're going to be talking a lot about non-abelian groups where this doesn't necessarily hold. But this week we're only talking about abelian groups, which are just sets, basically sets under addition, where addition works nicely. And so yeah, all of these things we've seen so far, the circle is an abelian group because you can add rotations of the circle together. The integers and real numbers have a nice addition structure. And so if we have an abelian group, and with this annoying topological condition called local compact, then we can define its Pontryagin dual as, and this is kind of complicated, the group of continuous addition-preserving maps between our group and the group of rotations of a circle, which I'm calling S1. And so let's see a few examples of this in action. So if we try and find the Pontryagin dual of the circle, we're looking at addition-preserving maps between the continuous addition-preserving maps between the circle and itself. And so what this ends up meaning is that you have a circle, and you have to kind of wrap it around itself in such a way that this point gets mapped back to this point in order for it to be continuous. So there's no kind of, it's not discontinuous. And so you can do that once. You can wrap it around once, twice, 3 times, and you can also go the other way, wrap it around 0 times, -1 times. And so the Pontryagin dual of S1 is Z. And on the other side, the Pontryagin dual of Z, we have to send 0 to 0 in order for it to be addition preserving. And then we can send 1 to any other point on the circle, and that gets us a unique addition preserving map, continuous addition preserving map, that is actually all of the addition preserving maps. So the Pontryagin dual of Z is S1. And it's generally true that the dual of the dual is the original group, and that's why it's called a duality. And then likewise, the Pontryagin dual of the real numbers, you can take R and you can take 1 to any point, but you can wrap 1 around the circle as many times as you want. And so it's not just S1, it's actually R again. And so this is the secret connection that lets us define the Fourier transform and Fourier series, all of that in a unified manner.
Could I ask a question about what is the wrapping that you're describing? Is that the group operation?
Yeah, so it's just the map that sends, like if you have a circle, it's the map that sends the angle theta to 2 theta.
Oh,
right? So you thinking about a circle, you think about disconnecting zero, you think about wrapping it around. As I've tried to illustrate here with this kind of like circle, a little spirally. But imagine these at the same point, because it's kind of hard to draw in 2D. And so now we can define the kind of general Fourier transform as a linear map from functions on an abelian group to functions on the Pontryagin dual group satisfying a generalized Pontcharel identity, which is just this equation here, which this generalizes the Parsifal's theorem, this generalizes the Pontcharel identity for real value functions on the real numbers. And so this is, I call this the almost general Fourier transform, because next week we're going to see the Fourier transform on non-abelian groups. But this is kind of where the magic happens. And this is what lets us build the Fourier transform for other abelian groups. Any question about that kind of high-level discussion before we get to other examples? Great. So let's get to another example. This is your new friend, Z mod n, where we just take a discrete set of samples and we can turn it into a abelian group by considering just this polygon and rotations of this polygon. So we can add 2 points together by just adding their corresponding rotations. And so as it turns out, the Pontryagin dual of Z mod n is itself, because we have to fix 0 in place, because addition preserving. And then we can send 1 to any of the other points in the group. And then we get another addition preserving map. And so, yeah, the dual of Z mod n is itself. And so, therefore, by this whole abstract theory we built up, the Fourier transform on Z mod n is an isometry from function on Z mod n to function on Z mod n. And so that kind of high-level overview allows us to actually just write it down. So this is the actual formula for the discrete Fourier transform. And since this is a linear map on a finite dimensional vector space, we can also just write it down as a matrix if this makes things easier. And once again, we kind of have this generalized Pontcharel identity between the function and its Fourier transform. And you'll see kind of a lot of similarities with the normal Fourier series and Fourier transform, that we've got these exponentials everywhere, and that gives you, this kind of complex exponentials give you the coefficients. So why do I keep on talking about this generalized Pontcharel identity? Well, now we're going back to actually what matters in quantum mechanics, which is that because it preserves the norm, what else do we know preserves the norm? Unitary matrices always preserve the inner product. And so as it turns out, this discrete Fourier transform is a unitary operation, which means we can implement it on qubits themselves. And so that's exactly what the quantum Fourier transform actually is. It's just the discrete Fourier transform on the state vectors, where you're treating the state vectors on functions as functions on the computational basis. So we can run through this example, right? This is the Hadamard gate. It's actually secretly, all along, it's just been a 1-qubit quantum Fourier transform. We can see this if we go back to this matrix. Omega is just, if we take the second root of unity, the primitive second root of unity is just -1. So n equals 2, it's just 1, 1, 1, -1, and then we have a 1 over root 2 out front. So the Hadamard gate is just the discrete Fourier transform on a single qubit. And as you could probably expect, this ability to implement it kind of natively on a quantum computer lets us get some kind of a noticeable speed up from classical algorithms. So if you just kind of do all of the multiplications and sums kind of normally, as you'd expect, you get a basic O of n squared runtime, where n is the number of samples, so 2 to the number of bits. Yeah, that's right. And then the Fourier, so classical improvement on the kind of naive method kind of exploits the subgroup structure of this z mod 2 to the n, where you split it up into two different Fourier transforms, and then there's an easy way to combine them back together. And so if you do that classically, you get this n log n that's kind of famous for being the runtime of the fast Fourier transform. And the quantum Fourier transform, because you can implement all of this kind of natively, it actually has a faster runtime of O of log n squared. And so we'll be seeing more of this like exploiting subgroup structure next time, where we talk about some kind of modern advancements in non-abelian Fourier transforms. But that is generally kind of the vibe of how these work. And using the subgroup structure, we can actually make a kind of, I haven't actually written out the kind of the gates of the kind of standard quantum Fourier transform, because this paper doesn't actually use the kind of what you'd see in a textbook. It uses this other algorithm where you exploit the subgroup structure to just read off the bits one at a time. And so this is kind of like measurement-based flavored kind of quantum computing. It's not really measurement, this is not measurement-based quantum computing, but you can see it's kind of, we're taking inspiration from these, like, using these measurements to read off the bits one at a time, and that saves us a lot of space when it comes to this algorithm. So this top part is just all equivalent to a quantum Fourier transform plus a measurement. And this is as it appears in the original paper. And if you want an exercise, yes?
Can you elaborate on what you mean by reading off one at a time?
So, right, the amplitude of the quantum Fourier transform, you're gonna see, like, it's just, when you do the quantum Fourier transform and a measurement, that's just gonna pick out a basis state of your computational basis where, you know, where the amplitude is, like corresponding to the amplitude after the Fourier transform. And so instead of doing the whole quantum Fourier transform first, and then doing a measurement to read off like a value of the Fourier transform, this is actually just mathematically equivalent to this, where instead of reading all the bits in one go, you kind of read off the bits as you go along. And so it's not intuitive that this should work at all, but we're using some kind of the kind of nice structure of the Fourier transform to actually make this optimization. I hope the next slide isn't sure. Oh, okay. Any questions on this discussion of the discrete Fourier transform before we go on to Shor's? All right, from Zoom, you guys alive? Okay, I guess not. So let's talk about Shor's algorithm. Shor's algorithm is kind of the headline maker. And in the education series, I said there were kind of two algorithms that are proven to have quantum speedups and that are actually useful. And this is one of them. So if you're given a number that's the product of two primes, Shor's algorithm finds what those two primes are. And this is something that's computationally kind of pretty intractable for a classical computer to do. It's not, I mean, it's obviously not impossible, but the runtime is much slower than you can get on a quantum computer. And so because it's kind of classically hard, because it's easy to multiply primes together, but hard to figure out what the primes are if you don't know them already, it's used a lot in encryption algorithms. And so this is responsible for all of these headlines about quantum computers breaking encryption. These are all just from last year. And every so often you'll see a new claim that's like, quantum computers are going to break encryption. But we're developing quantum-proof encryption faster than we're developing actual quantum computers that are capable of running Shor's algorithm. So, yeah, it's probably not going to be a big deal. Is how I see it right now. But we'll see. You know, it's only 5 years away. So the Shor's algorithm starts, and I'm just going to give an overview of Shor's algorithm. We start by picking an A between 0 and the number we want to find. And we're really free to choose A as to be anything we want. Generically, it's not going to share any factors with n. Because if it does share, but we're going to check to see if it does share any factors with n. Because that'd be really funny, right? If we just randomly picked an A and then it shared a factor with n. So we're going to check for that first. Then if that doesn't happen, which is likely, then we just go on to the next step. So once we have this A, the kind of big picture, and we'll see how this is implemented on an actual quantum computer, is that we know there's some R such that A the R is 1 mod n. And this is a group theory fact. I'm sure it can be proven without group theory, but this is just true. So we know n has to divide this product, whatever this product is. And so the idea is that, let's say n, so we know n divides this. If n doesn't divide either of these, we know p has to be in one and q has to be in the other. But we know p, q is hiding in here. So either they're both in this or they're both in this. And so if we're kind of lucky, then we have immediately that we could find the GCD of n with one of these factors, and this will give us p or q. And so basically this whole algorithm revolves around finding r. So if once we can find r, we can then just run this and get p or q. So then this is just the implementation of finding r, where we first construct this equal weight superposition. We have these two kinds of registers. We have the kind of result of this modular exponentiation, and then we have this kind of top superposition. And so first we construct this like even superposition on this first register of all these different states. And then we do this modular exponentiation step, where you see we map the state x0 to x a to the x, right? So this is a unitary operation. You'll see it, they include this kind of comment that it's the slowest step on a quantum computer, but it can be done. It's kind of not hard. That's what these U's are doing on this bottom register. U is an operation that sends x to ax. Like, it just kind of multiplies this register by a. And so you'll see we're multiplying by a bunch. Like it's some kind of controlled operation where we multiply by a bunch in this bottom register. And so when we do this with superposition, we now get this giant superposition of all of these a to the n for all n between 0 and big N. So now we get to actually doing the quantum Fourier transform on this first register. And since with the quantum speedup, this is actually the step that's slow on a classical computer. This is why you just can't do this on your normal classical computer, because it's this step that is traditionally very slow, but thanks to this quantum Fourier transform, we can do it very fast. And so after you do this quantum Fourier transform, you then immediately do a measurement, right? This is what I said the optimization was, where you can rewrite quantum Fourier transform plus measurement, and you can, instead of doing the measurement all in one go, you can do it as you go along. But the end result's the same. So after this quantum Fourier transform plus measurement, you get these peaks. And so you're much more likely to observe an outcome at one of these peaks. And so the point is that if you do, like this is the example of what you would measure if you did a lot of measurements on this, for example, from r equals 10. And this is actually from Shor's original paper, where Shor is outlining this whole algorithm. It's shockingly readable, I have to say, because it's back before we get all this technical stuff. It's back when you still actually kind of explain what quantum computing is. So it's actually kind of a nice read. But corresponding to r equals 10, we get these 10 peaks. And so if you can just measure the distance between the peaks, which you just do a bunch of measurements and then find the difference, you can compute r very easily. That's what all this mess about the continued fraction approximation, which is the algorithm. That's just what they're doing. They're just measuring the distance between the peaks. Okay, any questions about that kind of outline of the short time algorithm? Yes.
What does it physically mean to measure the difference, or like the distance between the two peaks?
So if you just perform a lot of measurements, you'll get a lot of measurements. All of your measurements will be at the peaks, because that's what it means to have a peak, is to have an opportunity for measurement. So let's say you get one outcome and it's here, you get another outcome that's here. You know that there are going to be multiples of some, like 1 over r. Like this is corresponding to r equals 10. This is like 0 over 10, 1 over 10, 2 over 10, 3 over 10, all the way up to 9 over 10. And so then you just figure out, okay, if we have all these, what's the most likely denominator for all of these measurements to fall under? Yeah, so okay, let me explain it a different way. So all of these are going to be out of 256 in this case, right? they're all going to be fractioned out of 256. So let's say you measure this one, and it's like, what does that look like? 25 or something out of 256. And you measure, this is like 100 out of 256. You find which denominator is most likely to have peaks at these with this kind of continued fraction approximation. So once you have the measurement outcomes, all the measurement outcomes, which are all at these peaks, this is something you can do pretty easily. Okay, I hope that answered the question. Any other questions about the Shor algorithm? So the kind of question that this paper wants to answer is that we were free to choose A at the beginning to be whatever you wanted. And kind of a question that experimentalists and like theoretical people both want to know is there a way to choose A kind of intelligently to kind of reduce the number of work that we have to do in order to factor numbers? And so that's what the paper I had you read this week answers. And so we can always choose an A such that the modular exponentiation register, so I told you there's these two registers, there's the QFT register and the modular exponentiation register. That bottom register requires only one qubit. And so this ends up simplifying our circuit considerably. This is all it is now. So this is the whole modular exponentiation, and this is the whole quantum Fourier transform. And so what this ends up being is what you end up measuring is always just a 50-50 outcome between 0 and 1. As these correspond to peaks at 0 and 1/2. And so if we have a 50-50 outcome, always, then we can just represent that as a coin flip. And so this is my QPU that I'm going to be running Shor's algorithm on. And to kind of demonstrate this, I'm going to factor this number using my QPU with this specific A value. So, okay, let's run this algorithm, right? Heads, tails, heads, 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 tails. Okay, so you got a pretty even mix of heads and tails. And so this means there's peaks at 0 and 1/2. And so if we find the common denominator that matches, we know the period, we know R has to be 2. And so incredibly, A has period 2. I mean, we just chose it, out of the blue, and somehow magically A has period 2. And so we can then find the GCD of A with n, A plus 1 with n, and that gets us this factor. The GCD of A minus 1 with n is this factor. And you can confirm, and I did, that these are actually the factors of A, the factors of n. This number factors into this times this. All right, now, does anyone want to come up and try factoring this number? Any volunteers? All right, come on up. I'll give you the QPU. And I'll give you the A value. This is the A value. Got it? Uh-huh. Okay. All right, how many times can you flip it? As many as you want. Yeah. Oh. Tails. 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 Heads. Oh, that one. Heads. Tails. Heads. Nice. So you get a pretty even mix of heads and tails. So those are your two peaks. Mm-hmm. So then the distance is 1/2. And so our period is 2. So A has period 2 again. And you can also check that these two have multiplied to n. I didn't write them out here. Yeah, sure. But as you compute it, A has period 2. So that's it. That's the live demonstration of Shor's algorithm for you guys. The only kind of slight problem with this algorithm is that you need to know P and Q in advance to kind of generate A. But it is always the case, there is always such an A, such that A is, so the way it works is that A is 1 mod P and A is -1, this should be mod Q. A is -1 mod Q. And so then you naturally have that A minus 1 divides P and A plus 1 divides Q, so the factors are in two separate, two separate numbers. And so this gets you that this GCD will always be P or Q, and it'll never fail, and it'll always have period 2. So this is obviously not a serious proposal, right? Like, if you know P and Q, then what's the point of running Shor's algorithm? But the paper has a very kind of important point to make, which is that basically every Shor's algorithm, every like published version of Shor's algorithm running on an actual computer at that point had always used an optimization like this. They've always picked A values that are nice, and they've never picked generic A values that would require more kind of more time to run. And so effectively what they're doing, I can actually provide a speed up of Shor's algorithm. This is my constant time factorization algorithm, shown here for 21, which has still not been factored normally by Shor's algorithm without these kind of choices of A. And I think this was true when the paper was written over 10 years ago. I think it's still true now. I really did check to see if anyone had done it, and I don't think anyone has. And so the kind of moral of the story is, what I always tell the education series, PR doesn't equal PR, press release doesn't equal peer review. But even peer review can be a little misleading, right? Because all of these, these were, 21 was published in a peer-reviewed journal, but it used this kind of A optimization to really simplify the algorithm. And so always be wary of people that try and show you a quantum algorithm on the street. Right. Any questions about the demonstration? About anything in the presentation? None whatsoever?
Okay, let me just give a very, very vague question, because I don't have very deep knowledge of this, but so the general Shor's algorithm requires this, this choosing of A,
Yeah.
and then you choose an S, so
Yeah.
and the S determines actually how many qubits you're using.
Where is it? Here. Yeah.
So, and is this the primary sort of obstacle, because just the difficulty of manipulating enough qubits?
Yeah, this Shor's algorithm requires a lot of qubits, and that's why no one's done it kind of legitimately. Because for a truly generic A, you need some large amount of pretty coherent qubits.
You have to constantly measure,
Yeah, this is even an optimization of over what Shor wrote. This is a fair optimization. The way this is written in the paper is legit. But yeah, it's inherently just a hard algorithm to run. Particularly when you get to the numbers where it actually matters, where it just n squared becomes ridiculous, and so s becomes ridiculous, and so little s becomes ridiculous, and now you don't know qubits is inflated. Anyone on Zoom have any questions?
Do you have one fill those charts? Could I upload the chat? Could I upload my question on the chat?
Oh, yes.
I guess in the meantime, can I also ask quickly about your justification for the live demo? And how
This is what they do in the paper. Yeah, so in the paper they actually do flip coins and factor these large numbers. That's where all the numbers came from.
Could you go to the slide?
All these numbers are ripped straight from the paper, including this one.
Or the slide before? Sorry, yeah, a little more. Yeah, like this.
This, yeah. Yeah, this is Shor's algorithm. Does Shor's algorithm distort our notion of quantum advantage? Is it scientifically meaningful to emphasize exponential speed up? This is actually a great question, because if we have these exponential speed ups, I mean, this happens in classical algorithms too, where we have speed ups, we have theoretical speed ups that'll never be realized because it's all O of n, and this is something I talked about in the education series, where even if it's got a smaller like O of n, it still might be slower because we're never doing anything at the level of n where it actually goes faster. Get a screenshot from. Wait, where did I see? Okay, thank you, Jamie, for proving I'm right. Yeah, so the paper makes the very explicit, answering Jamie, and I'll go back to Wonjun. Every Shor's algorithm to date has used some kind of a hacking, basically, to get the circuit to be much smaller. And so in general, I think, and people suspect, because exponential speed up, they're not like the little end of the 0.0001 little matrix multiplication speed ups that get published every few years. Being an exponential speed up, I think is, especially with Shor's algorithm, like quantum computers are only going to get better, and so we're going to eventually be at the point where it is faster to factor large numbers with Shor's algorithm over a classical computer. Just kind of the nature of quantum computers are not yet at their potential, and exponential speedups are just that good. But you are right to say, like, quantum advantage in theory and quantum advantage in practice. Well, even quantum advantage in practice and like actual usable quantum advantage are different, because like random circuit sampling is technically quantum advantage, but it's not actually quantum advantage because 2 is actually running random circuit sampling as a viable kind of useful quantum algorithm. I'm right again. Awesome, thank you, Jacob. Yeah, just always be careful with these claims that classical quantum computers have done something that takes classical computers in like millions of years to do. Because another funny thing that happens, this is completely kind of tangential to the actual talk, but another funny thing that keeps happening is that quantum engineers will pick these like kind of obscure problems to use for the quantum computing, like quantum supremacy demonstrations, and then someone always comes along and does the classical, like speeds up the classical algorithm because just no one had thought to optimize it before. Someone goes and speeds it up so that it's faster than quantum computing. I think we're finally like past that. It was like happening for like a good few years. I think we're kind of past that point though, but it was really funny while it lasted. Okay, well, if there are no more questions, thank you guys all for coming, and I'll see you next week for the non-abelian Fourier transform and modern algorithms for that.